Dear students, welcome to the class of real analysis, and we are studying metric spaces. We have defined metric space, we have seen some examples of metric spaces. Now we shall study limits in metric spaces. Now we know limit of a function in real numbers, or if f is a function from R to R, then the limit of this function we say as fx. Suppose the limit is L, then we may say fx approaches L as x approaches A. If for given epsilon greater than 0, there exists delta greater than 0 such that absolute difference of these two, fx minus L, is less than epsilon whenever the absolute difference of these two, means x and A, is less than delta. Whenever 0 is less than, absolute difference of x and A is less than delta. So this is the definition of limit of a function is L as x tends to L, and we write this as limit of f of x as x tends to A is equal to L. So fx approaches L as x tends to, or x approaches to A. Now the same definition we will write in metric space. So here the metric space, this is also a metric space, R and R, R to R, and we know the metric in R, that is R1, is the absolute value metric, that is x minus y. Distance between x and y is denoted by absolute value of x minus y, and that's why we are considering actually distance between fx and L. When we say fx approaches L, if the distance between fx and L is becoming smaller and smaller whenever the distance between x and A becomes smaller, and that distances are denoted by epsilon and delta. That means for given epsilon greater than 0, there exists delta greater than 0 such that absolute difference of fx and L, or absolute value of fx minus L, is less than epsilon whenever 0 is less than absolute value of x minus A is less than delta. And then we say limit of fx is L. So this is the usual definition of limit of a function that we have studied. Now how the same definition will be in metric space. Now instead of R, here we are considering M1, first metric space, and M1 with the metric defined row 1, and instead of this R we will consider the another metric. It is not necessary that the two metrics may be the same, may be different. So here the metric space is M1 and metric is row 1. Here the metric space is M2 and the metric is row 2. For different metrics, for different spaces, different metrics are defined as we have studied earlier. Now you see, here is the definition for limit in metric spaces. We have considered M1 with row 1 and M2 with row 2 are the metric spaces, and then a function f from the metric space M1 with row 1 to M2 with row 2 be a function. Suppose this is a function, and we say this function fx approaches L, where L is in M2 in this metric space, as x approaches A is in M1. If given epsilon greater than 0, there exists delta greater than 0 such that row 2 of fx and L is less than epsilon whenever row 1 of x and A is less than delta. Now see the difference in these two definitions. This is our usual definition and this is the definition in metric spaces. Now only the difference is of metric. The conditions are the same. Given epsilon greater than 0, there exists delta greater than 0. So here we have denoted the metric. Metric means distance between fx and L, and this distance is denoted by absolute value of fx minus L, and that is written here as row 2 of fx and L. That is also a distance in M2. The metric is row 2 for M2. is less than epsilon, and whenever the distance between x and a, but a and x are in m1 and the metric in m1 is rho 1, so rho 1 of x and a is less than delta. The meaning is the same. Whenever the distance in this m2 of fx and L, distance of fx and L in m2 is less than epsilon, whenever the distance of x and a in m1 is less than delta. So that is the same definition. Or if you consider the figure for this, see this is the usual definition we have. And now we will consider this metric spaces as, say, this is m1 with rho 1 metric, and this is m2 space with rho 2 matrix, and f is a function from this set or space, metric space, to another metric space m. Here, say this is a point x, and image of this will be fx, f of x, and we say as f of x approaches L, this point L, becoming closer and closer to L, whenever this x becoming closer and closer to A. And now the definition says that the difference between fx and L. Now this difference, or the difference, or you may say distance between fx and L, and that distance is less than epsilon, and it is measured by rho 2. Rho 2 of fx and L is less than epsilon. See the condition. And whenever the distance between x and a, this distance is less than delta, and this distance between x and a is measured by rho 1. So these are the different measures for m1 and m2. For m1, the measure we consider distance in terms of rho 1, and for m2 we consider the distance in terms of rho 2. And here for r and r, the same metric is there, that is absolute value metric. So therefore it is mod of fx minus L, or absolute value of fx minus L, and in this in this r, that is range, and for this r also it is the absolute value metric, the mod of x minus a, or absolute value of x minus a is less than delta. So the meaning of the definition is explained in this figure. So we refer this figure for the limit in metric space. And in this case, when this happens, whenever the distance between fx and L is less than epsilon, or the distance between fx and L is less than epsilon, whenever this happens first, when x approaches towards a, then fx will approach towards L. So that is written, whenever distance between x and a is less than delta, the distance between fx and L becomes less than epsilon. Then we say limit of fx is L as x tends to a, or we write fx approaches L as x tends to a. So the meaning of limit remains the same, only the change is we have used the metrics, respective metric, for denoting the distances. These are the points in m2, and distance is measured in terms of rho 2. These are the points in m1, and the distance is measured in terms of rho. So this is the meaning of limit in metric spaces. Now we shall consider sequences in metric space. Sequences in metric space. So a sequence in metric space M is a function. We know the sequence. What is the difference in the earlier sequences? We have considered sequences in real numbers, sequences of real numbers. That means the metric space is there R1, and here it may be in any metric space M. A sequence in a metric space M is a function. f from I to L, where I is the set of positive integers. And earlier sequence of real numbers we have, it is a function from I to R. Instead of R, here is M. And now for sequence of infinite sequence, we will define its limit. And we will write the definition for it. So if you consider a limit of a sequence, then we say a sequence Sn has limit L when given epsilon greater than 0, there exists n belongs to n. See, we suppose Sn is a sequence. Sn is sequence of real numbers. Then we have Sn tends to L as n tends to infinity. If given epsilon greater than 0, there exists n, capital N, belongs to I, such that mod of Sn minus L is less than epsilon for n greater than or equal to n. This is our usual definition. Now what will be this definition in metric space M? That we shall write. Let M row be a metric space, and let Sn be a sequence of points in M. That means Sn is a sequence in M. We say Sn approaches L as n approaches infinity. If for any epsilon greater than 0, there exists n belongs to I, such that. Now what will be the difference in the definition? The same words are there. You see, Sn is a sequence. Sn approaches L as n tends to infinity, or n approaches infinity if for given epsilon greater than 0 or any epsilon, whatever it may be, there exists n belongs to I, such that this is R, and therefore the metric here is absolute value metric, such that Sn minus L. This means simply the distance between Sn and L. And how to denote the distance in metric space? It is denoted by rho of Sn and L, such that rho of Sn and L is less than epsilon for n greater than or equal to n. So this is the only difference in the earlier definition of limit of sequence of real numbers and limit of sequence in metric space. In place of this absolute difference of Sn and L, we have written rho of Sn and L. Both has the same meaning, distance between Sn and L, and that distance here it is denoted by rho. So only the change is this rho. In place of absolute value of Sn minus L, we have written rho of Sn and L, and we write this as limit n tends to infinity of Sn is equal to L, or Sn tends to L as n tends to infinity. So this is the definition of limit of a sequence. Now we shall write the definition of a Cauchy sequence. And here we say this sequence is convergent. We say Sn, if it has a fixed limit, we say it is convergent. We say Sn converges. converges to L or to the point L in M. Now we define a Cauchy sequence. Now what will be the definition of Cauchy sequence? We know earlier definition of Cauchy sequence of real numbers. Sn is a sequence. Then we say Sn is Cauchy sequence if for any epsilon greater than 0 there exists. This is a symbol for there exists n belongs to I such that absolute difference of Sm minus Sn is less than epsilon for n both greater than or equal to n. So this is the earlier definition of Cauchy sequence. That means the difference of mth term and nth term is becoming smaller and smaller whenever m and n becomes greater than or equal to a certain number capital N. So this we have studied earlier. Same definition in metric space we shall write. So let again m row be a metric space and Sn be a sequence. Sequence of points in M. Then Sn is a Cauchy sequence. If for any epsilon greater than 0 there exists capital N as a positive integer, n belongs to I such that same conditions are there such that for epsilon greater than 0 there exists n belongs to I such that distance between Sm and Sn is less than epsilon. Now here that distance we have to denote in terms of this metric. That is the only difference. Such that rho of Sm and Sn is less than epsilon for both n greater than or equal to n. So this is the definition of Cauchy sequence. Here we have. And this is the definition of Sn approaches n as n approaches infinity. So thus we have defined limit of a sequence in metric space. We have defined Cauchy sequence in a metric space. Rho of Sm and Sn is less than epsilon whenever m and n are greater than or equal to n. Now there is a result that every convergent sequence is a Cauchy sequence. Now we write that result. We have proved that result for sequence of real numbers. Now here we will prove that result in metric space. And this will be a theorem. If Sn is a Cauchy sequence, is a convergent sequence, is a convergent sequence of points in a metric space, or convergent sequence in a metric space, then Sn is Cauchy. Or that means every convergent sequence in a metric space is a Cauchy sequence in metric space. So this is to be proved. Now we shall consider, let Sn be a convergent sequence, points in the metric space M. So convergent sequence means it has a limit. So we have defined earlier. Let limit of Sn as n tends to infinity is equal to L. And here L belongs to the metric space M. By definition of convergent sequence. And thus this means for given epsilon, or given epsilon greater than 0, there exist, by this definition, there exist capital N belongs to I such that rho of the distance between Sn and L is less than epsilon. So rho of Sn, instead of Sn we shall consider here as Sk. Term of sequence can be denoted by Sn, Sm or Sk. Rho of Sk and L is less than epsilon by 2. We will consider purposefully epsilon by 2. Epsilon can be taken at our choice. It may be epsilon itself, epsilon by 2, epsilon by 3, etc. And this happens for this k is greater than or equal to capital N. So this is the definition of limit we have written earlier. Distance between Sk and L is less than epsilon by 2 whenever k is greater than or equal to M. Now for we will take Mn both greater than or equal to capital N. We have, now see, I shall write here, for both M and N greater than or equal to M. Distance between Sm and Sn, that is rho of Sn, Sm and Sn is, see, this can be written as is by triangle inequality. You can say rho of Sm and L plus rho of L and Sn. So this is a triangle inequality. We have rho of x and y is less than or equal to intermediate point is z, rho of x and z plus rho of z and y. In z here, in place of z here, we have considered L, triangle inequality. And further, you see, M and N are both greater than or equal to N. So that means this M and N satisfies this condition. K greater than or equal to N, M also greater than or equal to N means M satisfies this condition. That is rho of Sm and L is less than epsilon by 2. Also N satisfies this condition. That is Sn and L, rho of Sn and L is less than epsilon by 2. And thus this is less than epsilon by 2 plus epsilon by 2. Or you may refer this as 1 and we write by 1. Or but this is equal to epsilon. That's why we have taken this as epsilon by 2. So after addition we get epsilon, and thus we have rho of Sm and Sn is strictly less than epsilon for Mn greater than or equal to capital N. And what this shows? This shows that the distance between mth term and nth term is less than epsilon whenever M and N are greater than or equal to capital N. This means the sequence Sn is a Cauchy sequence. Hence, Sn is a Cauchy sequence in M. In points in M, in the metric space M. See, and thus in a metric space M, convergent sequences are Cauchy sequences. In the sequences of in the chapter of sequences earlier, or sequence of real numbers, we have proved this result. Convergent sequence is Cauchy, and there we have proved Cauchy sequence of real numbers is also convergent sequence. That for sequence of real numbers or sequences in real numbers space, both convergent and Cauchy are the same. But here for any metric spaces, it is not the same, and we write it as a remark. there are some metric spaces where convergent sequence may not be a Cauchy sequence. In some metric spaces. Convergent sequence may not be a Cauchy sequence. So that means, so we have proved the result as convergent always implies Cauchy. Convergent, then it is Cauchy. But Cauchy does not imply convergent. So this is to be remembered, the relation between a Cauchy sequence and convergent sequence. So that is convergent sequence implies Cauchy, but Cauchy sequence does not imply convergent sequence. So this is in general. And for real numbers both are the same, but in general metric this does not imply. For example, let or consider the metric space. M, or that is the set of order pairs, means it belongs to R2 such that x square plus y square is strictly less than 1. This is the set we have considered, and because it is an order pair, that metric will be distance formula in 2 dimension with usual distance formula. With metric as usual distance formula. In 2 dimension as the metric. The metric is the usual distance formula in 2 dimension. Now let the sequence, we will consider the sequence A, 0, n divided by n plus 1, and see n takes value 1 to infinity. See, this is a Cauchy sequence, or you may observe n divided by n plus 1. If this is fixed to be 0, then it will be the first component is fixed to be 0, it will approach to 0, and n upon n plus 1 is a Cauchy sequence, in M, in this metric space M, but it does not converge to M. So why it does not converge to M? But it does not converge to a point in M. Why? Actually, this sequence converges to which point? The sequence A this sequence converges to the point. Now we can guess easily this sequence will converge to the point. This is fixed as 0, and this, as m tends to infinity, will converge to 1. So this converges to 0, 1 as limit n tends to infinity of n divided by n plus 1. This is equal to 1. Divide both numerator and denominator by n, so it becomes 1. This is also 1, and 1 by n tends to 0. That is 1 divided by 1 plus 0, which is 1. So this converges to the point 0, 1, but this point 0, 1 or the order pair 0, 1 does not belong to M. It is not in M. Why? Because in M the points are such that x square plus y square must be strictly less than 1. Since here what is x square plus y square? 0 square plus 1 square. It is 1, and 1 is not less than 1. So therefore this sequence converges to this point, but that point is not in M. But it is a Cauchy sequence. It is a Cauchy sequence, but it converges to point outside M, and therefore we say it is not convergent in M. So therefore A is not convergent in M, or we have written here it does not converge to a point in M. So this is an important relation between convergent and Cauchy sequence. Every convergent sequence is Cauchy, but every Cauchy sequence may not be convergent sequence in a given particular metric space. So this is about limits in metric spaces. The remaining part we will continue in next lecture. Thank you.